Valence bond theory. So we can describe the bonding that happens in complex ions using valence bond theory. So what's happening here is we've got a coordinate covalent bond. Instead of overlapping two half-filled orbitals, we're overlapping a completely filled orbital with an empty atomic orbital. In these complex ions, the empty orbital is always going to be on the metal ion. So the metal ion orbitals are going to be hybridized according to the geometry of the complex ion. This is just like what we did in 1A. We looked at Vesper theory and the Lewis structure of a molecule to see what its geometry was, and then we hybridized the atomic orbitals based on that. So if we have a linear geometry, it's going to be sp hybridization because we've got two things. Tetrahedral is four things, that'll be sp3. Now, square planar is one that we did not see in Chem 1A. But this is where you have a d orbital, an s orbital, and two p orbitals from that metal ion. And then the octahedral is d2sp3. So two d orbitals, an s, and three p orbitals. So valence bond theory explains the geometry that we observe, but it doesn't explain everything. It doesn't explain color or magnetism. So the complex ions form because the electrons on the ligands are attracted to the positive charge of the metal ion. But the ligand electrons also repel the metal's d electrons that are in the unhybridized orbitals. So when we've got octahedral ligands, they're going to overlap with two of the unhybridized d orbitals, and that's going to cause those two to have higher energy. The ones that overlap, and the ones that fall between are lower in energy. What the heck are you talking about? Pictures. Okay. So here we have these balloon shapes in the middle here are the unhybridized d orbitals, right? So we've got four of these things, and then we got the weird donut guy. And then here we're looking at an sp3d2 hybridization for the ligands to attach. So we have the points of an octahedron. So on this one, the ligands fall between the d orbitals, right? On this one, it falls between. On this one, they fall between. On this one, there's a ligand right on top of that d orbital. And over here, they're right on top of each other. And in this one, we've got overlapping with the d orbital along this axis. You see how that works? The octahedron and these five shapes of the d orbitals, they don't overlap very well. They run into each other. So these ones where the ligands overlap with the d orbitals, there's a lot of repulsion there because the electrons in that d orbital are repelling the ligand. And so that makes these higher in energy, and these are going to be lower in energy because there's not as much repulsion, because the ligand is further away from that orbital. So if we look at an energy diagram, in a free atom we have 5 d orbitals. They're degenerate, they're all the same energy. Here we're going to get orbital splitting, and we're going to have 3 orbitals that are lower in energy and 2 that are higher in energy. And we can measure the difference here, and we call that delta, the difference in energy. Any questions? So that delta is the crystal field splitting energy, the difference in energy between the two groups of d orbitals. How big that is, its magnitude depends on what the ligand is and also on the metal ion. So we call them strong field complexes when that splitting field is strong and the difference is large. A weak field complex, the splitting is going to be small, the difference in energy between those is small. So the reason that complex ions have such beautiful colors is because of that d orbital splitting. Color is related to the absorption of light energy by electrons. So things that appear black, like the bench top is black, that is absorbing all wavelengths of light. Something that appears white, like my mouse here or my Apple Pencil, is transmitting or reflecting all wavelengths of light. When we see something that's a different color, it's absorbing some light. Absorbs some visible light but transmits that color. Or it transmits most visible light but absorbs the complementary color. I think there's a word missing there. Because you can't absorb some visible light and transmit that visible light. So I guess what it's trying to say is, so this red one is going to be absorbing visible light but transmitting the red. You can also get that color by absorbing the complementary color. Here's the color wheel. So red and green are complementary colors. So something that appears red probably absorbs in the green region. TiH2O6 is purple because it's strongly absorbing in the yellow-green. So purple's over here, yellow is its complementary color. This compound absorbs in yellow-green. Here we're looking at the absorbance as a function of wavelength, and we can see it's right in this green and yellow region that it's absorbing most of the light. And so what we're seeing is the other colors. And we can use spectroscopy to measure the wavelength of light that gets absorbed when the electron makes its transition from a low energy to a higher energy orbital. And then we can actually calculate the crystal field splitting. So the crystal field splitting, that difference in energy, is going to be equal to the energy of the photon, which is hc over lambda. Lambda is the wavelength, c is the speed of light, h is Planck's constant, or Planck's constant times the frequency. So the complex ion, let's see, pentaamine nitro cobalt 3, I believe, is yellow. Estimate the crystal field splitting energy in kilojoules per mole for this ion. So if this complex ion is yellow, what color is it absorbing? It must be absorbing purple if it's appearing yellow. And this is not going to give just a precise answer, because this is, it's just looking, well, it's yellow. So let's just take the middle of the purple, right? It's from 400 to 430, so let's say it's absorbing at 415 nanometers. So yellow color, it's absorbing lambda equals 415 nanometers. So we want the crystal field splitting energy. Well, the energy here is going to be equal to hc over lambda. That's not a very good age. Oh, let's see if I can remember this. 6. No, I think it's 34. 6.626 times 10 to the minus 34 joule seconds. Ha! Ha! It helps that I used that in 1A this semester. Times the speed of light. There's an 8 in it, but not. 3.00 times 10 to the 8th meters per second. And then we're going to divide by the wavelength. What unit should we use? We should use meters, right? Because the seconds here are going to cancel, and we want the meters to cancel. So 415 nanometers is 415. What does nano stand for? 10 to the minus 9. So it's 415 times 10 to the minus 9 meters. So 6.626 EE negative 34 times 3 EE 8 divided by 415 EE minus 9. And I'm getting 4.79 times 10 to the minus 19 joules. Now, if this was a practice quiz or a homework question and you type that answer in, it's going to be wrong. Because here's my answer in joules. It wants kilojoules per mole. Right? This is the amount of energy for how many photons? 1 photon. 1 photon has that energy. Remember, light can be a wave and a particle, just like electrons. Yay. So this is equal to 1 photon. So we could say this is 4.79 times 10 to the minus 19th joules per 1 photon. So I need to convert that into moles. I'm going to put photons on the top because I want that to cancel out. And then I'm going to get joules per mole. So how many photons are in a mole? 6.022 times 10 to the 23rd per 1 mole. And then I can convert to kilojoules. Kilo stands for times 10 to the 3. But you see what I did there? I did it upside down because I'm zoomed in and I couldn't see this one over there. That'll be my excuse. Could also blame it on a slightly traumatizing thing that happened this morning, but I'm not going to tell the YouTube people about that. So it's also very sad. Okay, so we've got that 4.79, and then we're going to multiply by 6.022 times 10 to the 23rd, and we're going to divide by 1,000. And we're going to get 288 kilojoules per mole. And I don't think the answer's on here. So I was updating the slides, but I didn't get that far. Any questions? So we said that the ligands, the type of ligand affects the magnitude of the crystal field splitting. So this is called the spectrochemical series, and it lists ligands in order of their ability to split d orbitals. So these are the strong field ligands, and these are the small or weak field ligands. So small energy splitting, large energy splitting. And, we don't need to memorize that because it's a take-home test. Woohoo! The metal ion will also have an effect. A higher charge on that ion draws the ligands in closer. If the ligands are closer, then you have more repulsion, and so you're going to have a larger crystal field splitting. So that's the explanation of colors. Magnetic properties. So remember Hund's rule? Electrons will occupy degenerate orbitals singly when possible. So, if you've got some d orbitals, we'll just do the p orbitals. You got some p orbitals and you're sticking electrons in there. You put one electron there, and then the next electron, this is like going to a hotel where there's 3 beds, and you go in there and there's one guy sleeping in that bed. Where are you going to sleep? You're going to sleep in one of the other beds, right? Because why share a bed? These are not people that you know even, right? Why share a bed with a stranger if you don't have to? So you're going to take your own bed. Whoops. And the third electron is also going to take his own bed. The next one that comes in now has no choice. Now they have to start pairing up. But that's what Hund's rule says. Okay? So when the d orbitals are split, the lower energy orbitals fill first, and then the higher. So the next electron, after they're half filled, it's going to depend on the degree of the splitting. So the next electron can either pair with one of the lower energy orbitals, or it can go into a higher energy orbital. And which one it does depends on what the energy difference is between them. So this would be hexacyano iron 2, known to be dimagnetic. All the electrons are paired up. Remember, dimagnetic, 2 by 2, like the animals went onto Noah's Ark. Paramagnetic, that sounds like pair, as in pair of electrons, but it's spelled wrong. Di means 2. That para means opposite. So here we have a large crystal field splitting. So as we put these electrons in here, they're going to go 1, 2, 3, and then the next one is going to pair up. In the hotel analogy, which some of you guys know and some of you don't, you can ask me later. This guy's going to take a bed here because it costs a lot more to go into that next level, right? It's like, you're paying $100 for the room, and it's like $75 extra to go to the next level and get your own bed. And these guys are cheapskates, right? So they're like, I'll just tough it out. This one is paramagnetic. So this one has cyanide, which is a strong field ligand, causes the energy difference to be large. Water is a weak field ligand. This difference in energy is smaller. Now, they didn't draw it very well because it looks pretty much the same, but this difference is smaller. So now what can happen, actually I'm just going to write over these. So as the electrons come in here, they're going to take their own orbitals down there, and the next one's going to go up here. So this is like it's $1 to have to go into the next room. And here, this is $75 to go in the next room. It's a big difference, right? So just for an extra $1 on top of the $100 you're already paying, no big deal. We'll go in that other room and get our own beds. So now everybody's half filled. There's an electron in each orbital. Where does the next guy go? Well, he's going to take one of the lower rooms, or the lower beds, right? Less expensive. A less expensive, lower energy orbital, because is going to have to share no matter what. So both of these compounds have 6 electrons here. But in this one, they're all paired up. And in this one, most of them are not paired, right? This one's diamagnetic, and this one's paramagnetic. Yes?
So for that bottom one, if the gap was, say, large and not small, the bottom ones would be filled up first before that
Right.
top, right?
Yeah.
And
So if this was also a large field, a strong field ligand, it would do the same thing as this one. And that would just, 1, 2, 3, 4, 5, 6. And they'd all stay down there.
then figuring electrons is the same as any other.
Yeah.
Right?
Any other questions? Oops. So, complexes with strong field ligands will have fewer unpaired electrons, and that's what we just saw, right? This is a strong field ligand, and so we've got paired up electrons. This is weak field, and so this has more unpaired electrons. So the strong field ones, fewer unpaired electrons, those are called low spin. Weak field ligands are called high spin because they have, they actually end up having the same number of unpaired electrons as the free metal ion does. Not all metal ions have this high spin, low spin possibility. The metal ion has to have D4, D5, D6, or D7. 4, 5, 6, or 7 electrons in the d orbitals in order for that to happen. How many unpaired electrons are there in the complex ion FeCl6 3-? So what we need to find out is chloride a strong field or weak field ligand? So we'll go back and look at the list. It's over here, so it's on the weak field end. So, this is iron 3+. And so we need to look at the number of valence electrons. So iron is in the 4th period. So it's going to be argon, and then it's going to be 4s2 and 3d, 1, 2, 3, 4, 5, right? 3d5? Did I do that right?
Yes.
6? 1, 2, 3, 4, 5. Yep, 6.
Oh, yeah.
6. But it's an ion. So +3 charge has lost 3 electrons. So the first 2 that go are in there. Those are the valence electrons. And then the next one is in here. So we're going to end up with Ar 3d5. The d orbitals have 5 electrons. So this was weak field, right? So delta here is small. So then we're going to put the electrons in here. 1, 2, 3. Where's the next one going to go? To the top. 4, 5, and we're done. How many unpaired electrons? 5. Okay, cobalt and cyanide. Take a trip
What is this?
down here. Cyanide is strong field. What's the scale? This is energy going up, higher energy. So we've got cobalt, and what's the charge on this cobalt ion? 2 plus. So now we have to look at electron configuration for cobalt. It's right next to iron. It's got one more electron. And so when we make it an ion, we lose those two, and we lose one of these.
Is that 2 plus?
Thank you. We lose those two and nothing else. 3d7. So 7 electrons. And this one was strong field. So this is large energy difference. We're putting 7 electrons in now. 1, 2, 3. Where does the next one go? It's going to go on the bottom. They're going to pair up. It costs too much energy, too much money to go up there. So there's 4, 5, 6. Number 7 has no choice. It's got to go up there. So how many unpaired electrons? 1. Any questions? So that was for octahedral complexes. The d orbital splitting pattern is different for other geometries. In a tetrahedral geometry, the splitting is the opposite of the octahedral. So we've got 3 that are higher in energy and 2 that are lower. And it's usually high spin, meaning the delta here is smaller. Square planar gets ugly. So this happens in D8 metal ions. This is almost always low spin. But from our 5 degenerate orbitals, we get 2 that are degenerate, and then 3 that are on separate levels. Because this is low spin, these guys are going to fill up before they go up there. Any questions?